In this video, I introduced the chain rule. So let's review the derivative rules we have so far. We have the constant, the power rule, the exponential rule. We have all 6 trigonometric function rules. In each case, these rules, once you take the derivatives, you just get a function. There's no more derivative operator. That's very different from the other 4 rules we have currently, which are the derivative of a constant multiple, the derivative of a sum or difference of functions, the derivative of a product, and the derivative of the quotient. In all of these cases, to take the derivative of an expression, you do some common manipulation, and it leads to yet another derivative. But there's a number of function operations we do not have. One of them we're going to talk about today. So let's start with composition. Given 2 functions, f and g, like you see right there, here are 2 different compositions, f composed with g, and g composed with f. Notice that the order of the composition gives you different rules. Now for us, what we're going to be interested in is like kind of decomposing. I'll give you a function, and you want to recognize that function as a composition of 2 others. So given the function h of x, I want to find a function f and a function g, both in terms of x, that when you take their composition, you get the same rule. And one such answer is this one right here. Now there's more than one answer. This is just one particular combination. If you need to think about a way to view composition, it's sort of like a way for us to algebraically represent substitution by using functions. As you can see here, if y is the square root of u and u is x cubed plus 5, then y is the square root of x squared plus 5, which was what the function h was. So now that we've gone over composition, here is the chain rule, the derivative for compositions. If you have 2 functions, f and g, that are both differentiable and want to take their composition, assuming they're both differentiable at their corresponding inputs, then their composition is also differentiable, and it says that the derivative of the composition is equal to the product of the derivatives, each of them evaluated though at their corresponding inputs. So the derivative of f would then be evaluated at g of x, since that was the inside portion of the composition before anyway, and the derivative of g is evaluated at x. Now in leibniz notation, to make that look a little bit easier to digest, it basically says that if y is a function of u and u is a function of x and everything's differentiable, then the y is a differentiable function of x, and the derivative of y in terms of x is equal to the derivative of y in terms of u times the derivative of u in terms of x. Now I'll verify this at some later date, but for now let's focus on doing it. But I'd like to give you at least a physical example so you get a feeling for, it seems reasonable. A stereotypical, everybody does it example is the 3 gears. So you have 3 gears. 2 of the gears have a middle gear, so it's all linked together. Now you have gear A, B, and C. These gears will rotate. Gear A will move or rotate x times. Gear B will rotate u times, and gear C will rotate y times. Now I'd like to know how y and x and u all relate to each other. So if you look at y and u, every single time that the small wheel rotates twice, we have to get that the big wheel, c, will rotate once. So then u, the number of rotations for c, is equal to 1/2 u, the number of rotations for gear B. Using the same reasoning, you can see just by corresponding look at your different circumference of the wheels, you get that y must equal to 3 times u. By putting these together, you can then get y is equal to 3/2 times x. But if you look at the derivatives, the derivative of y in terms of u is 1/2. The derivative of u in terms of x is 3. By the chain rule, it says that the derivative of y in terms of x should just be the product of those derivatives, which is 3/2. And if you look at y, it's equal to 3/2 x. So the derivative of y in terms of x, in fact, is 3/2. All right, so let's go ahead and take this rule out for a spin. I want to know how to differentiate this function y in terms of x. First thing I would notice is, well, that thing is a composition. Composition is where you have a function of an expression. So here I would want to find out can I write y as a function of u? Well, yeah, I could write it as u to the 4th power, but where u is 3x plus 5. Notice I picked the function f to be the very last operation if you were to evaluate that expression for a given x. So then by the chain rule, the derivative of y in terms of x is just the derivative of y in terms of u times the derivative of u in terms of x. And I know what y is in terms of u. I know what u is in terms of x, so I can find those derivatives easily. So doing so, here's the derivatives. And I'll just clean that up by multiplying those. So you get 12u cubed. But I want the answer explicitly in terms of x. I don't want to have a u there anymore. But I know what u is, so I'll just replace it. So the derivative of this y in terms of x is 12 times the quantity 3x plus 5 cubed. So let's do it again. Well, I like to differentiate y is equal to the tangent of e to the x with respect to x. Well, notice once again, that's a composition, the tangent of e to the x. So the y is then equal to the tangent of u, where the u would be e to the x, and I know each of those derivatives. By the chain rule, the derivative of y in terms of x is the derivative of y in terms of u times the derivative of u in terms of x. Just cranking out those derivatives, you get that expression, and then I'll just replace the u with what it's equivalent to and write the product in a standard format. Remember, constants, monomials, binomials, and then we put the exponential usually next, and then finally we leave off the trig functions at the very, very end of the product. So you really should write the answer that way. So you've seen that the Leibniz notation is a great way to represent the chain rule. It's nice and clean, and it's kind of suggestive about the result because it's almost like the du's cancel. They don't cancel. Don't do that. But it does suggest that, and because of that, it helps you remember how to apply the chain rule correctly. But the Leibniz notation does have two disadvantages at least. One is it's not clear how to evaluate it. It's not function notation. We have f of. There's no of in there. So we don't have nice clean notation to evaluate it. We can write this if you really, really want to, but we often don't. So that's one bad thing. Another one is that if you want to use it the way I've been doing it, it's incredibly tiresome because you have to write down y as a function of u and then the u as a function of x. So we'll get around all that by doing this instead. This is a different way to write down the exact same chain rule because remember, y was f of u, so the derivative of y in terms of u is just f prime of u. That's easy. So what that suggests is this, is that if you ever want to take the derivative of a composition, there's an outside, that's the f, being applied to an inside expression, that's the u. It says, define the derivative of the composition. Take the derivative of the outside. Do not change what it's applied to. But then multiply, tack on, the derivative of the inside with respect to x. So let's do an example. I want to find the slope of the graph of the equation y equals e to the cosine of x at the point whose x-coordinate is 3 pi divided by 4. Well, e to the cosine of x, well, that will be a composition. It's e to the u, and u is the cosine of x. So the outside function is e to the u. So I'm thinking, to find the derivative of this outside function, I take the derivative of the outside function times the derivative of the inside. So specifically in this example, the derivative of e to the u with respect to x is just the derivative of e to the u in terms of u, which is e to the u, times the derivative of u in terms of x. Now with that rule as our guide, I want to know then what is dy dx. So I will apply the derivative operator to e to the cosine of x, and the derivative of e to something is e to that thing. That's the derivative of the outside function, but keeping the inside, and then I multiply it by the derivative of that inside. But the derivative of cosine is negative sine. So I'll write the answer as negative e to the cosine of x times the sine of x. Usually you want to write the exponential portion first and trig functions last. So the slope of the graph then is found by taking the derivative and just evaluating it when x is 3 pi over 4. So that would then be negative e to the cosine of 3 pi over 4 times the sine of 3 pi over 4. And that will then run you negative square root of 2 over 2 times e to the power of negative square root of 2 over 2. That's the answer. That's the slope of the graph at that point. Let's just do another example. Now, an object is going to be moving along a number line so that its position at time t is given by this particular formula. X is equal to the tangent of t cubed plus 4t minus 5. I'd like to know then what's the velocity as a function of time. Well, that's easy because we know that the derivative of position with regards to time, that's velocity. So all I need then is the derivative of tangent of a function of t. Well, but the derivative of the tangent of an expression of t, that's what u is, with respect to t is, you just take the derivative of the outside function. So the derivative of tangent is secant squared, but don't change the inside. So it's secant squared of whatever the u was. And then multiply it by the derivative of that u in terms of t. With this as a guide, let's just find the derivative. So our velocity function will then be the rate of change of that position. I can find that by taking the derivative operator and applying it to the tangent of t cubed plus 4t minus 5. And that would then be the outside's tangent. So this derivative is secant squared, but don't change the inside. Leave it alone. And then we tack on the multiplication of the derivative of the inside. So the derivative of the inside then would then be 3t squared plus 4. And you really shouldn't write the answer this way. You should put the polynomial there in front of the trig function. And this then would be the answer for the velocity of that object at any moment in time. Once more, just with a different application. So given the function f of x equals the cube root of x squared minus 4, let's find all x values so that the derivative either equals 0 or doesn't exist. Now remember, if the derivative is 0, then at that point the slope of the graph is 0, which means the graph has a horizontal tangent line. I've given you right here the graph of the function, so you can clearly see there's at least one horizontal tangent line. But maybe not so obvious, there's actually two places the derivative doesn't exist. Now those two places occur at 2 and negative 2. Now at those places, the tangent lines would actually be vertical, so there's no slope there, which means the derivative shouldn't exist. To verify that, here's the function. Now you've noticed that before when we took derivatives with radicals, we wrote them as rational exponents. I'm going to do the same thing here. That way you can now see it's a very simple composition of something to a power. So I need a rule for that. Well, the derivative of a function of x to a power in terms of x would be the derivative of that expression in terms of u, and you reduce the power by 1, and then you just multiply it by the derivative of the inside in terms of x. So let's just go and apply that rule. So the particular derivative would then be, I take the derivative of the outside function, which in this case is u to the 1/3. So it's 1/3 the power. I do not change the inside, the base. I reduce the power by 1, and then I multiply by the derivative of the inside. In this case, the inside is 2x. Let's just clean up that derivative to make it look nice. So that can be written as 2x over, you'd have 3 times x squared minus 4 to the 2/3 power. So if you want to solve, when is this derivative 0 for x? Well, the only way that could happen is if the numerator is 0. So then 2x has got to equal 0. That gives x is 0, which was, as I said, right there. That's the point. That's the point where x is 0. In another case, I'd like to know, where does the derivative not exist? So the derivative will not exist. Well, in this case, it's a fraction. If it won't exist if when you use a certain x value and the denominator is 0. So I'll solve when is the denominator 0. And clearly that means then x is 2 or negative 2 by just solving the equation using normal techniques. And that corresponds to right here in the graph, that's 2. And right here in the graph, that corresponds to negative 2. At those places, you have to have, in fact, a vertical tangent line. Just because the derivative doesn't exist does not mean you have a vertical tangent line. It just means it's a possibility. And looking at the graph, you can clearly see it's true. So as you probably have guessed, a lot of the derivative rules you already have chain rule versions. So all I've done right here is just write them in that format for you. The chain rule, though, results in yet another chain rule. So it's possible that derivative operator is applied to another composition. So you'll need another chain rule. Or you might have rules that go to other rules, or products that lead to quotients that lead to chain rules. So the derivative operator, d over dx, is just there to help you keep track of where you are in the process. If you can get the answer correct without using it, go right ahead and do so. But I find that most beginning students have a hard time doing so. Let me give you an example of having a repeated chain rule problem. Let's show that the rate of change of this function with respect to x is actually always positive. So, do so. I want to know the derivative of f in terms of x. So then I'm going to apply the derivative operator to the cotangent of e to the negative 3x minus x cubed. Well, that's a composition, cotangent of something. So I take the derivative of the outside function, that's negative cosecant squared of the inside, don't change it, leave it alone. And then you tack on the derivative of what was on the inside. But that now is a derivative of a sum or a difference. So then the derivative operator will then distribute through those pieces. So I then have the derivative of e to the negative 3x minus the derivative of x cubed. But that first derivative, notice how I keep copying down the same thing over and over again at the beginning, because that stays there throughout this whole process. The derivative of e to the negative 3x, that's a composition. So I need the chain rule again. So the derivative of e to the u is e to the u, so that'd be e to the negative 3x. And then I tack on the derivative of the exponent, negative 3x. But that derivative in terms of x is just negative 3. So I'll put parenthesis negative 3 to remind me to do multiplication. Then I have minus the derivative of x cubed, which is 3x squared. That's the derivative. The derivative operator is gone, so I know I'm completed the process. Let's just clean that up. Notice that's the same as writing a negative cosecant squared of e to the negative 3x minus x cubed times, I'd have a negative 3 e to the negative 3x minus 3x squared. But there's a common factor of negative 3 in the second factor of that product. So I'll take that negative 3 out, put it out front. I then have negative 1 times negative 3, that's 3, cosecant squared of e to the negative 3x minus x cubed multiplied to e to the negative 3x plus x squared. And you wouldn't write it that way. You would put this factor first in this particular product. So you'd have the constant and then the e to the negative 3x plus your x squared, then times your cosecant squared of e to the negative 3x minus x cubed. And that expression is certainly always positive because the cosecant is being squared. So we don't care what the cosecant is applied to. And e to anything is positive and x squared is positive. So everything here is a sum or product of positive numbers. Therefore, the result in the end, as long as it exists, is positive. Now, there are some specific ways that we use the chain rule with the product and quotient rule, specifically on how we simplify them, that you need to be aware of them. The big one, though, is for quotients. You never have to do the quotient rule ever again. You can convert every single quotient into a product if you want to and just do the derivative that way. The only time I wouldn't do this is probably trig functions. For example, what if I wanted to know this guy's derivative in terms of x? I would instantly just write this as 5 times x squared plus x plus 2 to the negative 3 power, and then the derivative that way. So the derivative of y in terms of x would then be 5 to the power, negative 3 to the base. I'd have x squared plus x plus 2. I would reduce the power by 1, and then by the chain rule, I would tack on the derivative of the base. And then I would continue from there. That then is 5 times negative 3 times x squared plus x plus 2 to the negative 4 power. And that's multiplied to the derivative of x squared is 2x, and the derivative of x is 1. So you just multiply the 2x plus 1. Now you go back and just clean it up. So the final answer would then be a negative 15 multiply the 2x plus 1. I would not multiply that. I would not distribute that product. And that's divided by x squared plus x plus 2 to the 4th power, because we don't leave negative exponents in our final answer. Here's a quick example of using the chain rule inside a product rule. So I'd like to know the derivative of this expression. So to do so, the derivative of f in terms of t is writing out slowly. I take the derivative operator and apply it to the product that I have, 1 minus 5t squared to the 4th power times e to the 3 halves t. That requires then, looking at it, notice the very last operation. If you were to evaluate this entire expression, the very last thing would then be the product between the two factors. That tells you the first rule should be product rule. So I have the first factor multiplied to the derivative of the second factor in that product plus the second factor times the derivative in terms of t of the first factor. There we go. Now I go back, and anywhere I see a derivative operator, I just do the derivative rule. So that would then be equal to, I'd have a 1 minus 5t squared to the 4th power. The derivative of e to something with respect to t, that would then be the e to the something, and I tack on the multiplication of the derivative of the something, the exponent in terms of t. Well, the derivative of 3 halves t in terms of t is easy. It's just 3 halves. So I'll write 3 halves. Then I have plus e to the 3 halves t. So the derivative of 1 minus 5t squared raised to the 4th power, that's composition. So I need the chain rule. That would then be the derivative of the outside. General power rule. I have 4 the power. 1 minus 5t squared, the base. I raise it to the 3rd power, 1 less than before. I then multiply it by the derivative of the inside, 1 minus 5t squared. That then equals, I get a 1 minus 5t squared to the 4th power times e to the 3 halves t times 3 halves plus e to the 3 halves t times 4 times 1 minus 5t squared to the 3rd power multiplied to the derivative of 1 minus 5t squared. That is negative 10t. And don't forget to put the parentheses and maintain the product. That's the derivative. But we're not done. You have to go back now and clean this up. You just can't leave it that way. So general rule is you write every product as a constant, then monomials, then binomials, and so on, saving exponentials and trig functions for last. So I'd first rewrite this as 3 halves 1 minus 5t squared to the 4th power times e to the 3 halves times t. In the second product, I'd have a 4 times a negative 10. That makes a negative 40, or minus 40. I have a t, so I'll put that next. Then I have 1 minus 5t squared cubed. I'll put it next. Then finally I have my exponential e to the 3 halves t. Now that's the derivative. But still, I would not leave it that way, because one of the things we almost always do with derivatives is set them equal to 0. So we want to get into the practice of setting it up to make that step easy. In the product rule, there's always a sum or difference of products. Between those products, there might be common factors. If there are any, you take them out. So this then would be, I have at least a 1 minus 5t squared cubed as a common factor. I have an e to the 3 halves t as a common factor. And then it's hard to see, but see the fraction? I'm going to take out some kind of fraction out of each of these products. So what's left over will just be integers. In this case, that would be a half. So let's see. Divide a half into 3 halves, you get 3. 1 minus 5t squared to the third divides into 1 minus 5t squared to the fourth and leaves 1 minus 5t squared. Notice the power is only 1. And then e to the 3 halves just cancels with the e to the 3 halves. Then you have minus 40 divided by a half. That's actually 80. And then the 1 minus 5t squared to the third just cancels with itself. And the e to the 3 halves, t, that also cancels. So that's what's left over. Notice what's left over is really nice and simple. So we can easily just multiply that out and simplify it. So the final answer then would be that the derivative of f in terms of t is going to be a 1/2. I'd have 1 minus 5t squared, that quantity cubed, times the expression. Let's see, I have a 3 minus 80, and I have a 3 times a minus 5. So it's a minus 15t squared, and then I'd have a minus 77. And that's then multiplied to an e to 3 halves t. I probably wouldn't even leave it that way. See in the factor how there's a common negation? I'd probably take that negation out. So if I just go and erase that minus and I erase that minus and make it be a plus, I can put that common negation out front. And that's the final answer to this particular problem. I can go over so many more examples for derivatives, but I think as you were watching me do it, you probably noticed I was being very, very careful with how I wrote things. That's because the proper reading and writing of notation and just having a thorough understanding of the order of operations will go a really long way to successfully doing a derivative. Let me show you an example. Here are 3 functions. Y is the tangent of 3x squared, y equals the tangent of 3 times x squared, and the tangent squared of 3x. In these 3 examples, you need the derivative of tangent somewhere, but you need to know when to apply the rule in order to go and get the derivative correctly done. So in the first one, second one, and the third one, I just want to see or talk about what derivative rule you would use first. Because if you can't figure that out, of course you can't do the problem. Here, the first one, the derivative of the tangent of 3x squared. In this case, the outside operation, the last thing you would do if you evaluate that expression would be the tangent. So this is the tangent of something. So the first rule you would use is the tangent rule. In the second one, though, that derivative is actually a lot simpler because of where the parentheses are. The tangent of 3, that's just a number. This is a constant times something. So you take the constant out, and you would take the derivative of x squared afterwards. That's different from the next one, the tangent squared of 3x. Here, the very last operation is actually the square. You could write this if you want as tangent of 3x. This entire thing squared. So the outside rule is actually u squared. So you use the general power rule first. So just keeping in that same vein, let's suppose that you have function f and g and their derivatives with respect to x have the following values as given by this table at x equals 0 and x equals 1. I want you to evaluate the functions at the values that I give you. So in the first example, if h of x is 5 times f of x minus 2 times g of x, I want to know what the derivative of h is at 1. Well, by the derivative rules, the derivative of h with respect to x would then be 5 times the derivative of f at x minus 2 times the derivative of g at x. So then h prime of 1 would then be 5 times f prime of 1 minus 2 times g prime of 1. But from the table, I know what those are. The derivative of f and g at 1 are negative 1/3 and negative 8/3. So that'd be 5 times negative 1/3 minus 2 times negative 8/3. And that would then be 5/3 plus 16/3. That's 21/3. 7 is the answer. So the next one, same idea. I have f of x plus g of x. I want to know h prime of 0. Well, doing the derivative rules, then h prime of x would then be, that's a composition of f with something. So it's the derivative of the outside. Do not change the inside. So you have x plus g of x. And then multiply it by the derivative of the inside. So the derivative of x plus g of x, the derivative of x is 1 plus g prime of x. I'll just go back down and replace every single x with a 1. So just giving some more room over here on the left, h prime of 1 would then be equal, h prime of 0. H prime of 0 would then be f prime of 0 plus g of 0. Then I have times 1 plus g prime of 0. But I know what those values are. That's f prime of 0 plus g of 0. That's just g of 0. And g of 0 is 1. So that's f prime of 1. And then I have times 1 plus g prime of 0. But I know what that is. G prime of 0 is the third. So that would then be, that's an f prime of 1. 1 plus 1/3, that's 4/3. So I had 4/3 times f prime of 1. But f prime of 1 is negative 1/3. So that would then be 4/3 times negative 1/3. That is negative 4/9. And that's the derivative of h at 0. And that gives you a basic overview of the chain rule derivative for composition of functions.